And who are you and what do you do?
That's the first part. All right. Can folks see this?
Yes.
Yep.
Great. All right. So, hey, everybody. For those of you who don't know me or I haven't had the pleasure of meeting yet, my name is Jonah Edwards. I run the core infrastructure team here at the Internet Archive. Even some of those of you who did work on site maybe never got to see the extent and scope of our deployment. Those of you who have come in remote only definitely haven't been able to see a lot of it. So what I'm kind of hoping to do here today is just give you an overview of the sort of operation we run, a sense of the scale of the thing, and a better understanding of the nuts and bolts and kind of a better framework to ask questions from. So there's no cloud. It's just someone else's computer. Most of us have probably heard this sentiment in some form or another. But here at the Internet Archive, that's really, there's no cloud. It's just our computers in our buildings run by our people. And it's run by the core infrastructure team. So in the context of the Internet Archive, what is core infrastructure? I have some pat answers I give, we're behind the APIs, or where the bits live between bits in and bits out, full stack engineering, we're the rest of the stack. But really what we do is design, maintain, configure, deploy, and help all of you interface with the physical reality of storing data at the Internet Archive. We have around 750 operational servers right now. We run these things way longer than anyone else does. The oldest systems in our fleet are from back in 2012. More than 1,000 VMs across the fleet, which is probably what those of you who interface with us directly mostly interface with. Tens of thousands of storage devices from high performance NVMe flash, SSDs, the spinning disks underlying the operating systems on the servers, and over 20,000 spinning disks in paired storage, which is the redundant storage layer underlying the Internet Archive's corpus, totaling nearly 200 petabytes of raw storage capacity in the Internet Archive. Probably some of you have seen this graph before. This is charting of disk growth. We've been fortunate in the last few years that there's been a significant increase in hard drive sizes. You can see that just kind of within the last 18 to 24 months, we've been able to double the size of the primary hard drive in our fleet from 8 to 16 terabytes. So even though we were pretty much flat in terms of number of hard drives for 2020, scaled to drive size, storage volume continues to grow very significantly. We're currently growing the Internet Archive by over a quarter of its size per year. This picture you can see here is 10 petabytes of hard drives getting loaded into the data center. That's going to be about 5 petabytes of paired storage, under 1/4 of what we bring in each year. We're hoping that we're going to be able to move to 20 terabyte hard drives later this year, but there's kind of a technological crunch happening right now that's keeping hard drives from increasing in size as quickly as they have for the last couple of years. So, we'd love to be moving to 24 or 30 terabyte hard drives with heat assisted or magnetically assisted recording technologies, but may not happen this year. And there's a big question for us of new storage models. Is paired storage kind of the right approach? This is not 100% accurate, but these are kind of 5 principles that we've really been able to rely on for decades at this point. Items in the archive, they're directories on disk. The basic unit of storage is the disk. Disks are replicated, content is served from everywhere, and we roll things forward as disks age out, as they start to fail, we move them forward to new, larger disks. It works pretty well. And the simplicity of this model really lets us get down to the weeds. When we have problems with hard drives, we're able to figure out exactly what happened. There's not a lot of abstraction above it. That's good and bad, but for an archive, it makes sense. We want to know exactly how our bits are being stored. So at current disk sizes, with the 16 terabyte disks we use, it would require 15 racks of servers to house 1 copy of the Internet Archive. We're running currently about 75 racks of servers. Not all of those are 16 terabyte disks. We're still running some 4 terabyte disks that are trucking along. And of course, not every single one of those racks is hosting data in paired storage. So how do we get the data out to the world? We've got it. we've got it. We want people to see it. As you can see, graphic design is my passion. But we've had a huge explosion in outbound traffic over the last year. With the pandemic lockdown, you can see there in March and April of 2020 how we really flatlined just because demand increased so quickly and so dramatically, much faster than we anticipated. And so, our goal is to serve as much as we can, as fast as we can, as cheap as we can. And we do that by having multiple data centers and serving from multiple sites. So we're currently, this is kind of our site layout around the Bay Area. Probably most of you are familiar with 300 Funston. Some of you have been to 2512 Florida Avenue. Fewer of you have been to 380 Carlson. That's primarily a physical archive at this point. We're starting to work on the data center build out there now. And then 200 Paul down there at the bottom, I just want to kind of give a little shout out. As far as I know, only 4 people at the Internet Archive have ever been there. Only 2 of us have been there more than once. It's a very exclusive club. This is their nice photo from the outside, but this is really what it looks like on the inside when you're making cross connects to other folks on the internet. 200 Paul is where we do it. We connect to 2 what are called tier 1 providers that give you access to the internet at large, everyone out there. And then, does my video gonna work? Let's see. This is what it looks like when routes move around on the internet. So we receive full routes to the entire internet from Cogent and Hurricane Electric. We're connected through the California Educational Network. That's mostly to academic and government sites. And then our friendly local nonprofit internet exchange, SF Mix, connects us to other folks in the Bay. Let's see if I can move this slide forward. Yeah, there we go. This is kind of again, graphic design, my passion. You can kind of see the flows out to the internet at large. This is a snapshot from yesterday. We're pushing 60 something gigabits out most of the time right now. We're currently working on expanding that capacity. My expectation is that flow will be probably in the 80 gigabit range once we kind of clear everything out here, and then just more from there. So the inter-site links that we do are kind of our current bottleneck. We run those with a technology called dense wave division multiplexing. I'm not going to get too into this. I just think it's super cool. So I tell people about it whenever it comes up. We use fiber optics to connect our sites. And just like with a prism, if you shine the fiber optic in different colors, you can prism it together into a single beam of light and deprism it back at the other end. Super cool technology. Anyway, that's my little aside. What we're moving towards now is actually going to be a full fiber ring between our sites. We're going to have 100 gigabit links between all the sites. We are going to be able to utilize both directions of the fiber ring simultaneously, giving us kind of 200 gigabits of bandwidth in both directions. Of course, if we use the whole thing, then we're not going to get quite the redundancy of the fiber ring. And that's the reason I'm really excited about it, is that's been kind of one of the biggest causes of outages for us, especially long-term outages. We have here, you can see the North American fiber detector. If you want to know where the fiber is, just run a big drill and you will find it. And then aside from that, we've kind of had, occasional power quality issues. You can see those down there at the bottom. It's not great. We don't like that, but those are generally resolved pretty quickly. And then I just wanted to kind of show a little bit of the physical infrastructure that goes into making these inter-site links and getting all our data centers connected so that data can flow around. This is it, folks. This is a 100 gigabit fiber strand popping up out of a manhole. This is what the internet is made of. If you're a really cool organization like we are, you have your own custom branded manhole covers. Took an arc welder to that one. And then I kind of wanted to just show a little clip of new fiber construction. If you're not just pulling it through underground conduit, you've got to dig up the streets. So for the last link of this new fiber ring, that's exactly what we did. And here's a little demo. This is what the internet looks like, folks. We're heading down Clement, turning up Funston. Our neighbors love us. All this was dug up, repatched. Don't worry, we only have to go a few blocks. This is really hard to do in the city of San Francisco. You can see where they're still patching it. I had to resist the urge to make a little Internet Archive logo potato stamp and drop our sign in the wet concrete. And here's where they haven't started the patching process yet. We make it all the way up to Lake Street here. And here's the underground box that we're spliced into. So that's what the internet looked like. Musical credit, great 78 project. Thank you, Sydney Beckett and his New Orleans feet warmers. And I'm ready for any questions you might have about the terrible reality of physical infrastructure.
I have a question and a comment. So I'll start with a comment. So you're the people that I can't stand to rip up all the roads and just patch on over. So just putting that little plug in there.
It's me.
It's you. But who pays for all that construction work? Is that like a combination of us and San Francisco, or like?
So that's exactly right. In this case in particular, because we're a library, we have access to FCC funding to get connectivity. And this kind of falls under that umbrella. So we're working with a fiber company. We pay a little bit, the FCC pays a lot. So whenever you're looking at your cell phone bill, there's that little FCC accoutrement line at the bottom, and you're helping us dig fiber lines.
That's great to know. Thanks.
Questions,
Jonah?
comments?
Jonah, who's on the team that's providing all the support for core ops?
Yeah, so it's a great group of people. They're not glory seekers, but my team is Trevor Von Stein, Johnny Martinez, Andy Bozzella, and Steve Carmian. And then there's a lot of other folks kind of working on the core side behind the APIs. Sam, Hank, Jim, Joe, Aaron. It's you may know us. If not, stop by ops sometime. We're always in there.
Thanks for all you guys do. I know it's not a small task to keep this spinning and the data flowing.
Jonah, this seems completely insane. Who could possibly have imagined we wanted to do things this way? And so the idea, everybody else is moving to AWS. What's some of the pluses and minuses you see in that realm?
I mean, the minus is cost, straight up. And there are other minuses. Big ones for me are control of the system. If someone has a problem with what we're doing, they have to come and talk to us. And that's how I want it to be. User tracking is a big one for me. Amazon probably doesn't track users, but they absolutely could. And as a library, that's kind of anathemic to me. But really, we don't run the numbers that often. The cheapest tier of storage in Google Cloud and Amazon is Glacier or Coldline. And those are broadly offline storage models. You can't pull all the data out at once. It's not all being served live. And we are still somewhere between, depending on how you count, 2 and 5x cheaper for us to store data than to store it there. And we're online all the time. I mean, most of the time. We got 3 9s and an 8 last year, but they're in the right order, so I'm happy. Anyone else? Well, yeah.
It's always kind of wild to me that, from my perception, the cost of bandwidth to basically anywhere in the world, like if we're sending a book to India or we're sending a book to Oakland, it costs the same to us. At some point, do we hit a size where we start paying differently for bandwidth, whether it's going under a transatlantic cable or not?
Kind of. What that really would look like would be At that scale, the demand for the content from us is high enough that we would be able to directly negotiate peering agreements with tier one providers. Right now, we pay for bandwidth to the internet at large. We kind of pay a flat rate. We pay less for bandwidth to academic sites and even less for kind of, local folks who want to connect to us directly. But there is a scale at which, and that scale is in the terabits out, where that's, Netflix style. But there is a point at which that does happen. Absolutely.
Jonah, I have a question. I'm curious what happens when things go out, because it could go out because of all sorts of different reasons, and all we know is that it's out. So when that goes into ops, what do you guys do to figure that out?
Oh man, I mean that could be a very long conversation. I mean, by and large, we kind of do a very quick initial process of elimination because we know what makes big outages for us. It's power issues and it's connectivity issues. If one of us gets paged in the middle of the night and we go to log in and we can't even get to the servers, the servers are offline for one reason or another. And then we kind of track it from there. Otherwise, it's, hash it out in ops, dig through logs, all of the usual, living in a terminal instead of in a graphic design world, which is honestly where I'm more comfortable.
Jonah, I have a question. This is Jefferson. I'm curious about both the operational realities, but also your editorializing on the challenges of greater drive density, because going, from 4 to potentially 20, and it's just a lot of data and paired and in a small footprint. And what does that mean? And where is the risk threshold end up falling as drives get bigger and bigger and bigger?
Exactly. So there are kind of a few facets to that. One of the biggest ones really is because of our use as the disk drive as kind of the basic unit of storage. It means that when we fail a storage unit, we have to replicate it. And that's the thing that at some point stops scaling. This happened already in the context of parity-based redundant arrays of independent disks, kind of back in 2007 through 2010, when a disk would fail, you had to reconstruct it from parity information on adjacent disks, and then suddenly you're putting every other disk under high load, you fail a second disk. We're not there yet, and actually our replication time has gone down as we've moved to the 12 and 16 terabyte disks because they're actually much more highly performant than our 8 terabyte generation was. So we know what a good ceiling in the form of the 8 terabyte disks, and assuming disks remain comparably performant to the ones we're seeing now, we could probably get up to the 24 to 30 terabyte range before we hit the replication times that we saw in the 8 terabyte world. So we've got a runway, but there's also some architectural changes that are going to come down probably in the next 2 to 3 years. All right. You can always find me on Slack. I'm around.
Can I add a second answer to Jefferson's question?
Yeah.
Another factor that comes into play as our data density increases, our storage clusters also double as compute clusters. And so as the amount of data on a given rack increases, that ratio shifts, and we begin to have more of a crunch in terms of being able to do the processing we want to do on the data with the equivalent amount of hardware. And there can also be bandwidth issues, which Jonah is doing a great job of staying ahead of. But had he not done all the work that he's already done, the amount of data that we have on these disks now, we wouldn't be able to deal with it getting in and out of the same number of servers and racks. So it does sort of cascade and cause pressures on the rest of the infrastructure.
Related follow-up and point to what you just said, Hank, is Jonah, what is the density of cores or speed of cores, like if you had a similar kind of graph, or what is ops finding like that we can buy for a similar price for the chassis? Is it going up? Is it just only a little bit?
Yeah, so we basically kind of rev our server design roughly every 3 years-ish, sometimes a little longer. And this is pretty approximate, but we probably find core performance to 2x over that interval. We're exploring right now, very much focusing on kind of ways to add computational performance in places other than just like CPU throughput. A big part of that is higher performance flash storage. The entire full text search engine now runs on high performance NVMe, and it's worlds of difference. Rolling that out for other components of our infrastructure will allow us to kind of improve that performance within the same, close to the same physical footprint, a slightly higher power footprint. Similarly with GPUs that we're exploring right now, which is really, really exciting. You know, there's a ton of what we do is that exact form of highly parallelizable sort of kernel-based computation, especially in the derived world, as you know, Tracy. And so that's a big thing for us. The challenge there will be that we've built out our data center infrastructure with a pretty narrow electrical and cooling envelope. And so figuring out kind of how much we can wedge into what we've got will be kind of key to balancing that.
Jonah, I have a question about architecture. A lot of people are seeing the end of the Intel architecture long past what I had hoped it would last, and switching to ARM because of its great power to cooling and storage model and density and just general advantages. Are we thinking about that for the next rev of servers?
My guess would be the rev after the next rev. You know, the field of ARM chips right now is extremely heterogeneous. And so kind of settling on a specific ARM core is going to box us in potentially in ways that we don't fully understand yet, but particularly with the power efficiency, we definitely can't ignore it. It's absolutely going to be something that we want to move towards. I'm kind of, you know, it's fun to be bleeding edge, but you know, if I want to run a computer for the next 9 years after I buy it, I want to make sure it's the right one.
I have a quick question about costs and you know, you had mentioned 24 terabytes and it's scaling, and like what are the alternatives coming, and is, you know, what is a rack cost? I mean, the amount of storage is continuing to scale, and it sounds like that's going to continue over time. What is that cost, and are there going to be alternatives in the future that will bring the storage cost down?
It's kind of variable. You know, we saw, like, a great example over the last year. I remember being in a meeting just a little bit over a year ago that I think Brewster mentioned on Monday, where we realized that we had to pre-buy a bunch of stuff because supply chains were going to get shaken. So normally we expect the cost, hard drives are the dominant cost of our capital outlay. And normally we expect those to kind of decrease in a reasonably predictable way. That didn't happen for much of last year, although it's kind of happening now. So the real issue, I guess I would say, is that hard drives are fundamentally consumable, which means that we can't lag a generation behind on hard drive technology like I would prefer to do from just a cost effectiveness perspective. You know, previous generation typically comes with economies of production, economies of scale, but in hard drives, once the next one comes out, they stop making the old one. So that's kind of the place where we're stuck buying current revs. I don't have numbers for costs on hand, but we could chat about that.
I just wanted to jump in and just give a shout out to the group that pulls this together. It is a phenomenally hard thing to do, to basically run your own servers. Basically, people don't do it anymore, but we do. And it gives us cost advantage, it gives us control advantage. And there's some disadvantages, but you know, we don't have access to all of the cool new widgets that AWS. But there's a reason why AWS and Amazon has got the highest stock price in the globe. It's because of profit they make off of other people that we don't have to participate in. But the work that's done towards keeping this level of infrastructure going is super hard. But the total number of racks hasn't increased that much over the last 10, 15 years. It's slowly going up because the hard drives aren't getting big enough, bigger fast enough for us. But the number of hard drive, the whole total number of total hard drives has not gone up all that much. Some of the new cool things that that Jonah and his group and working with the development group, the programmers on is SSDs, which are super fast hard drives that don't spin. There's GPUs, which are graphical processing units. These are like having a supercomputer inside your computer. These are NVIDIA chips. You may have seen this type of talk of neural engines and all of that kind of thing. We're going towards machine learning, and we're experimenting with that. We upgraded to 10 gigabit networking throughout, but we're still operating these 9-year-old machines that get us back into the gigabit time frame, and these guys have been able to not throw things out. It's so easy to go and say, oh, I just don't want to deal with that old stuff. It's like, you've got to deal with it. And so there's all these generations that are being maintained by the same very, very small group. I'm really impressed that we're able to get to the 100 gigabit per second outbound connections. We just signed the check for 200 gigabit routers, and we're starting to test RAID systems. This is a redundant array of independent disks. We do our replication on 2 different machines, but very simple on a disk by disk basis. We're doing experiments of trying to make it so that it's more maintainable, so they don't just have to, the machines could not just be across town, but in a different country. We're all built on Linux and the wonder of open source. And it's just, what a sharing, awesome, amazing environment. The whole Linux, Ubuntu, free and open source software, the sharing that's been going on. And then we built the Petabox infrastructure on top of that, mostly in PHP and Python, to go and offer our services to the world. It is a really impressive thing that this group has been able to pull off.
Agreed. Thank you all so much. Really appreciate you listening to me nerd out. Like I mentioned, I'm on Slack. If you have any other questions or want to chat about anything, just let me know. I'm around.